Hi everyone, in this video we are going to review the module Nuclear Energy. So the way I do my reviews is I typically split the material into two different sections. I have a context section and I have a chemistry section. So the context section is going to be your facts, as the things that you just have to memorize. There's no way around it, you just need to know all these little bullet points, okay? The chemistry section is more of the application side. It's where I throw a lot of the hard math at you, or the application, right? So the good thing about nuclear energy is that the application section and the chemistry section is actually quite small. The bad part is that means there's a lot that you have to memorize. So for this module, I would highly encourage you to do the best you can to get all of those facts down, because it's a lot of memorization. Alright, so let's dive right into it. Enough of me talking. One thing I do want to point out though is at the very end of this video, I'm going to have 3 of what I consider to be the most difficult math problems. So if that you want some extra practice, just zip to the end of this video and you'll be able to see those. Alright, so let's start from the very beginning, which is our context section. So number 1, context. So like I said, the context section is going to be the section I expect you to memorize. These are all of your facts. So let's start off very simple. We started off by discussing the history of nuclear energy. Okay, so you need to know some facts, know the very minimum things that I pointed out. After that, we discussed the difference between a chemical and a nuclear reaction. And so now the difference was actually pretty much in 2 different categories. The chemical section, we said that energy released is usually about 500 kilojoules per mole of fuel burned. And we know that the change in mass is always 0. So if we have a certain mass on the reactant side, we're definitely going to have the exact same mass on the reactant side. So our mass is conserved. However, for a nuclear reaction, that is very different. We would say a typical nuclear reaction releases anywhere between 10 billion kilojoules per mole and even higher. But for this one, we say that mass is not conserved. And this right here is the exact reason why we study nuclear reactions at all. Because there's a change in the mass, it is able to be converted into this insane amount of energy, which is awesome and which is why we study. Alright, so after we solidified the difference between chemical and nuclear reaction, what we moved on is what we discussed, the nuclear power plant. Okay, so we talked about this a lot, and so I'm going to group everything here together just for simplicity and kind of organizing it in your brain. So for the nuclear power plant, the first thing we did is we drew out the schematic. So I would highly recommend that you can draw this out and make sure you can explain every single aspect of it, and make sure you understand the difference between the primary and the secondary coolant system. That's a very important section. Alright, after we discussed the actual, just the operational standpoint of it, we discussed the fuel source, so nuclear fuel. Alright, we talked a lot about this, the assembly, what the fuel rods are made of, what the pellets are made of. You need to know all of it, absolutely all of it, and make sure you can draw it, okay? Now, we know that nuclear fuel highly depends on chain reactions. If we don't have chain reactions, we can't have a nuclear power plant, which means you need to understand what chain reactions are, and I would be very comfortable with the one I kept showing you, with starting off with U-235, okay? We also then talked about a radioactive decay series. And the one I showed you and kept showing you was the radioactive decay series for uranium-238, so I would be comfortable with that one. We also talked about what we did with our waste, our nuclear waste, specifically the ones that came from fuel. So the ones I really focused on was our SNF, our spent nuclear fuel rods, okay? You absolutely need to know the other categories as well. There's 3 of them. Make sure you have all 3 down. After we talked about nuclear fuel, we moved back kind of to the global topic of the power plant, and what we focused on were the differences between a nuclear explosion and a chemical meltdown. And so just to review, even though I know you all have this down by now, we have only experienced chemical meltdowns. We have not had a nuclear explosion at a nuclear power plant. A nuclear explosion is when we drop those atomic bombs and we killed 80,000 people, okay? That is not what happened at these chemical meltdowns. We talked about 3 specific cases: Fukushima, Chernobyl, and 3 Mile Island. You need to know the details of all of those, okay? There's a lot of facts in this unit. You just have to get it all down. Alright, after this, we talked about what was possible for terrorists, especially if a bad guy came in and tried to get some of our fuel. So we focused on the difference between a nuclear reactor and a nuclear weapon. Okay, so there's a lot of things that we just compared the differences between, and I'd make sure you know the difference. We now know that a nuclear weapon needs very, very pure uranium-235, and they need 90% of it in order to have, 90% of your fuel source needs to be pure uranium-235 in order for you to have a powerful weapon. For a reactor, remember, we only need 3 to 5% of our uranium-235. The fuel sources are very, very, very different, so make sure that stays solid in your brain. And then the last thing we did in the nuclear power plant schematic or section is that we reviewed at the very, very end the major differences or the global differences between a coal and a nuclear power plant. Okay, so I would make sure I'm very familiar with that list and know which ones they both have, which risks they both have, and which ones they have individually. So after we talked about the nuclear power plant, we also moved out to more of a global topic, which was radiation. And so for radiation, again, we've already talked about radiation in terms of electromagnetic radiation, but now we are talking about 3 other types of ones. And so the biggest thing was when we introduced the term radioactivity. And so we started talking about elements that spontaneously decay into other elements. So they convert, they change their number of protons, they change their prototype, okay? So now, after radioactivity, we talked about a specific type of radiation, which was our ionizing radiation. Ionizing radiation is the really, really high energy radiation. That's your gamma rays, your X-rays, and the high energy UV rays. And the last thing we did is we talked about our normal human or a human person or a human being here out on planet Earth, their background radiation. So what are you exposed to on a daily basis? And I do expect for you to understand that the biggest natural cause is radon, and the biggest human cause is medical procedures, specifically those CT scans. Please, 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 for the rest of your life, no, I always want to limit the number of CT scans I have on my body. All right, so that was the contact side. From there, we moved on to the fun part, which is the chemistry side. And sadly, in this module, the chemistry section was actually quite small. But what that means is that you need to know every single one of these next 5 topics or whatever it is very, very well. There's no excuse for you to not know these. You know it's going to be a bulk of the exam, so you want to make sure you know every single section here. And to start off, you better make sure you know what an isotope is. I would know the definition, I would know the standard notation, I would know every single thing you could possibly tell me about what an isotope is, because that's everything that has to do with nuclear chemistry. Now, once you understand isotopes and you know what they are, be sure that you can balance nuclear equations. So remember, that just means that the subscripts on the left side need to equal the subscripts on the right side, or the sum of them. And the same thing with your superscripts. We need to make sure your mass numbers are the same and your atomic numbers are the same, okay, overall. After that, we needed to make sure that we could break this into 3 different categories. The first thing for balancing a nuclear equation, you need to be able to identify what is considered an alpha, a beta, and a gamma particle. Okay, you just need to be able to look at something and say, oh, that is definitely an alpha particle. Now, after you do that, you would need to be able to look at a nuclear equation and tell me, was that alpha or beta decay, if it was one of the two, okay? So I would expect you to balance the equation, identify the particles, and tell me, if it is, what type of decay that is, okay? Now, the last thing we want you to be able to do is, after looking at a nuclear equation, is be able to use the mass effect to actually determine how much energy was released from that explosion, from that awesome nuclear equation, okay? So we need to make sure that you're very, very comfortable with Einstein's theory of relativity. After that, we did some fun math by converting from the 3 different units of radiation. Or I should say 4 different units of radiation. The first one we looked at was rem. That's the old one. We don't really use that very much anymore. Then we looked at sieverts. Those are very, very much more common. We also looked at rads, and at the very, very end, we looked at curies. So I'd make sure you know all 4 of those, and make sure you can convert from one to the other if you were asked to do so. I would also make sure I know definitions of those, okay? The last thing, which is personally my favorite part, and that's because it has a little bit to do with kinetics, but I didn't really go into that too much, so don't worry about that, is we started calculating half-lives. And the reason we did this, the main purpose we did this, is because we were able to actually talk about carbon dating, or your C14 dating, carbon 14. All right, this right here, out of everything we did in this class, that is your biggest real-world application, okay? We hear carbon dating. We hear about people talking about carbon dating all the time in the news. You also hear of skeptics talking about it. And so for me personally, one of my biggest goals for you is I want you to be able to talk to someone about carbon dating, know what it is, and then just walk in and drop some knowledge on them and be like, I'm a genius, right? Yeah? Maybe? No, okay. All right, so that's all I have for the review. That's it, right? That's a fairly short module. module, but there's a lot of memorization. You need to get those facts down, and you need to make sure that you can do every single one of these things that I pointed out here in the chemistry section, okay, and very well. If you don't have it down, email me, talk to your teacher, but we need to make sure you get this down before you approach the exam, all right? All right, so now what I'm going to do here is move on to the 3 hardest questions that I personally think are the most challenging out of this unit. And so the first one we're going to do here, number 1, is what nuclide is formed when thorium-234 undergoes beta decay. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. The first thing that you should do when you look at this problem is identify the fact that there's 2 pieces of key information. They tell us your reactant, which is your thorium-234, and then it also tells us that it goes through beta decay. So we know that our thorium is going to convert into some other element, plus it's going to emit a beta particle. So now we know our beta particle is an electron with a 0 for the mass number and a -1 for our charge or our atomic number, right? So now what we have to do is fill out one more piece of information, which is the mass number of thorium. So what you would do is look at your periodic table and say, okay, that has an atomic number of 90. Now you're ready to solve your equation and actually answer this question. So the first thing you do is look at your bottoms, look at your subscripts. You know you have a 90 on the left side, so you know you have to have 90 on the right side. So we're just going to pick some variable x plus and -1 or -1. The only value x can be has to be 91 in order to solve that mathematically. So we're good here. Now we see that we have to balance our superscripts or our mass numbers. So for thorium, we have 234. That's equal to some variable y plus 0. So this is a really easy math problem. The only value y can be, it has to be 234. The last step, which is probably the most important step, is you need to actually identify that element or that isotope. So what I would do is I look at that subscript, I see that it's 91, and then all I do is I look at my periodic table and figure out which element has an atomic number of 91, and what you would see is that you have, it's Pa or protactinium, an element that I never say, but it somehow keeps showing up when I do these questions. So that is the answer. So if we asked you this question on the exam, you would say the answer is protactinium-234. Or if we asked you to put in the notation, hopefully you would write it just like that. Okay? All right, question 2. Number 2. How much energy is released from a nuclear reaction with a mass defect, very different, of 1.0 times 10 to the -4th kilogram. So it's really, really tiny. We're just looking for the energy here. Go. All right, did you get an answer? Hopefully you did, but the one thing you need to realize is that I would absolutely, on an exam, I would absolutely give you the constant, which is speed of light, 3.0 times 10 to the 8th meters per second. You probably already have that memorized, and if you don't, it's a good thing to memorize, but please know on an exam, I will always, always, always give you that constant. So now, why do you need that constant? Well, the only way you can solve this problem is by using Einstein's theory of relativity. So you have E is equal to mc squared. We're primarily concerned with mass defect, so we're always going to look at that delta M. So we're looking for energy. Our mass defect was given to us, 1.0 times 10 to the -4th kilograms. Here's your red flag. Always, always, always make sure that your mass is in kilograms. If it's in grams or micrograms or anything else, you have to convert it, okay? Watch out for that on the exam. Now, C, speed of light, 3.0 times 10 to the 8th meters per second. You have to square it. Don't forget to square it. If you type this in your calculator properly, you will end up with an energy equal to 9.0 times 10 to the 12th joules of energy. That's huge. That's so much energy released, okay? That's your answer to the question. Hopefully that made sense. Again, if it doesn't make sense, email me. Let's make sure we solidify this before you take that exam. All right, last question. And personally, I think this is the most challenging, but it just depends on how your brain works. So a fossil contains 12% of the original fraction of carbon-14. How old is the sample? Okay, I'm going to give you one piece of information. We're going to say that the half-life of carbon-14 is equal to 5,715 years. We're going to use the date provided to you by your book, your textbook, okay? Go. All right, did you get an answer? Hopefully you did, because we did a similar problem to this earlier in the videos when we looked at radiocarbon dating technique, okay? So the first thing that you do here is you figure out how many half-lives it takes to get to 12% of the original sample. So I always start off with the same chart. All right, you have 100% of the sample at the beginning. First half-life, you cut down to 50. That's one half-life. After you're at 50%, once you go through another half-life, you just cut that in half. That's going to be 25%. So that's your second half-life. After you're at 25%, you need to cut that in half, and you end up with, ding, 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 12.5%. So 3 half-lives. So what we're saying here is that this fossil has 12% of its original sample of carbon-14. So it has undergone 3 half-lives. So now we're looking for a length of time. So how old is the sample? All you do is you take your number of half-lives times the actual half-life, so 5,715 years. If you do this properly, you get an answer something like 17,145 years old. It's a really, really, really old sample. I hope that makes sense. If it doesn't, please, please, please email me. Ask your teacher. Google help sheets on nuclear equations and radioactive decay, and you can absolutely find extra problems here to practice this, okay? Good luck on the exam. Take care of yourselves and drink so much water.